Did you guys look at that third homework problem? Yeah. So I only assigned 3 because I thought that third one was pretty tough. It's not. The way I was proving it was making it pretty tough. Oh wow. Someone's left behind 2 entire sticks of Haggeroma chalk, which is like $1 a stick and the best chalk in the whole world. And I'm gonna use it. So yeah, it's 1H.7, is it, or 9? Do you remember? 7? Yeah, so here's what you had. You have a triangle. Is A this vertex? A, B, C, maybe? And you're told just draw on any old two line segments. So connect B to this side AC. Maybe my labeling scheme is not quite right. And connect C to this side over here. Okay, so that gives us points. I believe they were P and Q. Again, maybe I'm not labeling the right way around. But then what I'm going to do is I'm going to come in here to point P, or sorry, yeah, let's go point P. And I'm going to draw the line segment that's parallel to CP, or CQ rather. So this guy's parallel. So, and I'll connect that to, again, maybe I'm getting the labeling wrong, but X. So PX is drawn to be parallel to CQ. These letters definitely don't seem right to me, but and I'm going to come into Q and I'm going to draw on a line segment that's parallel to BP. Okay, so let's call this Y. So QY is drawn to be parallel to BP. And what you want to do is show that this line, XY, show that XY is parallel to BC. And so how do you think we'd proceed? Well, obviously we have a similar image to a lot of the stuff we were doing in the section, right? With this lemma that says that if you draw a line segment in one of these triangles, then it's parallel to the base if and only if the ratio of the corresponding sides are equal to each other. So that should be what you're thinking about doing. The question is, how are you going to do that? And my thinking was, okay, I want to show that these sides are proportional to each other, so I need to show similarity between this triangle here, AXY, and the whole thing ABC. How am I going to do that? Well, I know they match up at this angle, so if I could just show another angle matches, AA, we'd have similarity. And I didn't quite realize that once you establish this, if I establish that this angle is the same as this angle, then I've already shown that these two lines are parallel. Because they're corresponding angles, right? This is a transversal cutting through these two lines. If these two corresponding angles are equal, then of course they're parallel. So anyway, I set out with this goal in mind, and in the process you can show lots of things. You can show this triangle here and this triangle here are similar. This triangle here and this triangle here are similar. You can show that this guy is a quadrilateral, or not a quadrilateral, of course it is, 4 sides, is a parallelogram. And in doing all of that, you can show that this triangle is similar to this triangle. And then you can invoke exterior angle theorem on some stuff and show that, okay, this angle must be the same as this one. A lot of work. And I really suspected there was an easier method. So I asked our grader, I went to Niall, and I said, Niall, what am I missing here? Find me an easier proof. And he pointed out to me that I am missing a much easier way to proceed. I really like this proof though, because it really just works from first principles. But he pointed out to me that there were 2 triangles I wasn't even thinking about, which is this triangle BAP and this triangle is contained inside of it, QAY. What do I know about that? Well, inside this bigger triangle, I've got this smaller triangle where this line is already told to us to be parallel to BP. Right, so invoking the lemma, since this line is parallel to the base, I know that the ratio of the corresponding sides are equal, right? I know that, yeah, I definitely haven't labeled this the right way around, but in this picture, I know that AQ, the length of this side, AQ over AB, must be the same as AY over AP. AY over AP. Right, just looking at this triangle and the smaller one inside of it, where I already know this line's parallel. So by the base, I know this is similar to the bigger one. So I have this ratio, but you can do the exact same thing with this other triangle here. You can go AQC, right, this triangle, and inside of it is a smaller one, where I know this line right here is parallel. You can come up with a similar ratio for that guy, and just playing with those ratios, you get the result pretty quickly. So I won't fill in all the details for you, but a much, much easier method of proof. Meanwhile, what I was trying to do originally was really show just about every single property that you could possibly think of involving all of this stuff that's happening in here. So not nearly as hard as I thought. So I'll leave you with that. Again, don't use my labeling here, please. Use the one that the textbook goes with. Yeah, maybe it was ABC. But with that, we'll pick up where we were last time, which is talking about the circumcircle in a little bit more depth. And what do we have? We have the extended law of sines, right? We have the extended law of sines that told us that this ratio in the law of sines is actually equal to some fixed constant. Of course it must be. But that fixed constant is related to the triangle itself in the way of it's equal to twice the circumradius of the triangle, or the circumdiameter, if you want, of the triangle. What else do we show? We showed that the perpendicular bisectors of a triangle, they're all concurrent at a single point, that point being the center of its circumcircle, of the triangle. And since we looked at intersection of perpendicular bisectors, let's talk about intersection of just altitudes in general, because it turns out altitudes intersect at a single point. So consider the following. And unfortunately, right now we're going to restrict our attention a little bit more than is actually necessary, just based on what we know. We're going to work with an acute angle to the triangle. What do I mean by this? Obviously, I mean all the angles are acute. So all angles less than 90 degrees. And let's draw, man, this chalk is nice. Draw an altitude AD and extend AD to intersect the circumcircle at point X. Okay, so I've got an acute angle triangle, A, B, C. And what we're doing is we're coming into this triangle, we're looking at angle A. Notice all the angles here are acute. We're coming into A and we're drawing the altitude from A. So something like this, that's probably a right angle. What did I call this? I call the altitude AD. So the labeling there, I'm suggesting that this point on BC where it intersects, that's going to be point D. And we're going to extend this. We're going to extend this line until it hits the circumcircle. And the point where it hits the circumcircle, we call X. How do I know that my altitude actually passes through BC? Right, remember, you can have triangles that look like this. Here's A, B, C, and if I draw an altitude from A, well, that doesn't pass through BC. So why does that not happen here?
You would need angle C to be greater than 90.
Yeah, so because it's acute angle, because it's an acute triangle, it has to pass through BC. So that's not a problem. The other thing I'm going to claim is that AD is bigger than DX. Why? Why is that? So why must D be closer to X than it is to A?
Since angle A is acute, the arc BXC is smaller than the arc BAC, so it's like further along the circle.
Yeah, exactly. It needs some formalization. Even what I'm going to tell you right now needs some formalization. But remember from last time, because angle A is acute, that means that this side, BC, lives sort of on the opposite side of A, or sorry, on the opposite side of the circumcenter as A does, right? So because BC is sort of on the opposite side of the center, it's not too hard to convince yourself that D must be closer to X than A. Formal argument would be something like, consider the perpendicular bisector of AX. Perpendicular bisector of AX must be parallel to BC and passes through the circumcenter. Right? So this is already halfway along the line, and I know that this point here, D, must be further along. So okay, so we have this. And what I'm going to do is I'm going to come in here, I'm going to measure this distance from D to X, and I'm going to go backwards along this line. I'm going to go backwards along this line the same distance, and I'm going to call that point H. Doesn't look quite the same distance in my drawing, but that's okay. So AD is bigger than DX, so choose H on AD so that HD is the same length as DX. Another way to think about this is just calling H is the reflection. It's the reflection of point X through this line BC. Right? So it's just lives on the other side on the perpendicular bisector and the same distance away. All right. What we're going to do now is we're going to draw the line segment BH in, and we're going to extend it until it hits the circumcircle. And in doing so, it meets two other points, or two other lines. So it cuts through AC at point E, and it hits the circumcircle at point Y. So we're going to draw BH and extend it, and extend to points E and Y, where the extended line meets the side AC and the circumcircle respectively. So as always, my drawing isn't quite perfect, my drawing isn't quite accurate, but what I want to claim is that this line we've drawn is a very special line in this triangle, and that it's also an altitude. It's the altitude drop from B. So this is our claim. Claim BH is perpendicular to AC. I suppose really I mean B, but same thing. Our textbook is sort of ambiguous on this sometimes as to the author will mention a line segment like BH, and when I see BH I think of just a line segment, but he really means sort of an extended line segment. So that's what I mean here. This extended line segment passing through BH is perpendicular to AC. And essentially we'll prove this. I suppose that's what we're doing now, or we're stating a theorem and proving it. Okay, proof. What do I know about this point D? Well, by definition of H and X, it's the midpoint of this line segment HX, right? Just because H was chosen so that this distance here is exactly this distance here. So D is the midpoint of the line segment HX. And this angle we've drawn, the one angle I've indicated here, HDC, of course I could go with any angle. So how would I just call it angle D? Because they're all the same. Angle D is 90 degrees. What does that mean about the relationship between these two lines, BC and HX? BC is perpendicular to HX, but it's something more than that. Since it cuts right through the midpoint, it's the perpendicular bisector. All right, so it's more than just being perpendicular. So BC is the perpendicular bisector of HX. What does that mean? Well, that means that in particular, B is equidistant. B is equidistant from H and X, right? So that is, maybe I shouldn't say that is. So it follows then. Let's just say this means. This means that B is equidistant I can't get over how good this chalk feels today. You guys are familiar with Hager and Wood chalk, right? It's like a cult following for this stuff in mathematics. What do they say about it? I don't know. Something about no one ever uses Hager and Wood chalk once or something. Once you use it, you're hooked forever. And there's a big thing where the company that makes this was stationed in Japan, and just when people in sort of America started finding out about this chalk, they decided to shut down. So mathematicians went online and just hoarded boxes and boxes of this stuff. People bought like enough chalk to last them the next 30 years, the rest of their career. And then people started sort of dealing it. They would sell it to their colleagues. Here, you want a box? I got 30 years of boxes. I'll sell you a box for whatever. And anyway, some guy in Korea pretty much bought, the entire company bought their formula. And now they're making hydrorama chalk, and it's identical to the original stuff. So these people have 30 years of boxes stashed away when you can buy it on Amazon again. But anyway, this means that B is equidistant from H and X. B is equidistant from H and X. We'll say i.e. what I care about is BD is equal to, no, not BD, BH is equal to BX. That means that this triangle BHX is very special. What type of triangle is it? Isosceles. Hence, triangle BHX is isosceles. And this implies that BD, again, this is a right angle here, BD being perpendicular to the base, it's an altitude, but we've seen that for isosceles triangles, altitudes, at least altitudes to the base, are the same as medians, but also the same as bisectors, angle bisectors. So this implies that altitude BD is also the bisector of angle HBX. So we have then that these two angles here, those two angles are congruent. Angle HBD is equal to angle XBD. HBD is equal to angle XBD. And I'm getting a little bit tired of writing words, so I'll just put an implication sign here. What does that mean? Well, this angle, I've written it as HBD, but if I think of it as YBC, same angle here, that's an inscribed angle, right? And that subtends this arc. Meanwhile, DBX is the same as CBX, that subtends this arc. So those two arcs are equal in angle measure. So arc YC is the same as CX. So YC is equal in measure to, I wrote XC in my notes, so we'll call it XC. Okay, we're just about there. The question is, and this is sort of one of the interesting things about proofs in mathematics, is the question is, why am I doing all this stuff, right? Remember, I wanted to show that this is a right angle. In fact, I think I don't end up showing this one that I've drawn. AEB. I actually end up showing this one's a right angle, but of course they're all the same. What I wanted to do is, of course, show that this is a right angle, right? To show that these are perpendicular. So why am I working with all this stuff down here? Well, the reason is because proofs in mathematics aren't usually written in the same way as you originally think about these things. So if you're originally thinking about this problem, you're going to be thinking, I want to show this is a right angle. How am I going to do that? Well, I have two intersecting chords. Right, I've got these two intersecting chords, and I know how to measure angles between intersecting chords. Right? We had this theorem way back, I don't know if it was way back when, maybe 2 weeks ago, that said that the angle between two intersecting chords is the average of of their subtended arcs, right? So this angle right here would be 1/2 of AB plus YC. So somehow I need to measure these things, right? And the way we're going to do this is actually this way. So finally, here's what we're going to do. 90 degrees. What's that equal to? Well, that's equal to one of these angles down here. I'm going to go with ADB. Thank you. Okay. All right, so 90 degrees is equal to ADB. And these are two intersecting chords, right? So I can measure these angles in terms of their subtended arcs. ADB would be 1/2 of AB and XC. AD plus XC. And I really should put equal in measure.
You mean AB?
AB, thank you. All right, so this angle here, I know this one's 90, right? By assumption, this one's 90, and that's the average of these two arcs. So the observation is, and you'd make this before you start writing any of this stuff, is that I can actually almost relate these two angles. This one looks very much like this one because at least subtends 1/2 of the same arc. Unfortunately, this guy subtends YC and this guy subtends CX. But we went through all this work to show that YC and CX or XC are actually the same in measure, right? So all I'm going to do is make a substitution. This is, of course, the same as 1/2 of AB plus XC. No, not XC. That's not an interesting observation, just writing the two things are equal. XC is YC. So by all that work above, we have this equality. And AB plus YC, 1/2 of AB plus YC, that is the angle we're looking at. That's angle AEB. Which establishes our claim, right? That establishes that BH, well, extend it, go BE if you want, BE or BY is perpendicular to AC. So, establishing that BH is perpendicular to AC. So it's sort of one of the problems with mathematical proofs. I don't know if it's necessarily a problem, but everybody wants their proofs to be clean, right? You just want everything to follow logically in order. Unfortunately, when you're working through these things and trying to figure out why things are true, that's not usually the way you proceed, right? You would just sort of start off and say, well, I want to show this is a right angle. Okay, well that right angle is related to these two, this angle is related to these two arcs. And then, if you're clever enough to see it, you might see, well actually, I can show that this arc is the same as this arc, and therefore this angle must be the same as this angle. Which isn't at all the order that we wrote it in the end. But suppose, yeah, I won't write any of this stuff, but you can then play the same game with the other vertices and drop all of their altitudes, and you'll show that those also pass through at H. So H is a very special point. It's called the orthocenter, and it's the point of concurrence between all the altitudes of at least an acute angle triangle. It's actually true for all triangles. But yeah, so H is called the orthocenter. Of triangle ABC. And all altitudes are concurrent at H. What we've done is we've proven that this is true for acute triangles, it's true for all triangles, but we'll have a much better way of showing that in just a few sections. So we'll revisit this then. I'll tell you another fact about it, it's the unique point. It's the unique point in triangle ABC that lies on the circumcircle when reflected through any side. And so what I mean by that is there's other points in this triangle, that I can reflect through, say, this side here that would live on the circumcircle, but it's the unique point that when you reflect it through any side at all, it lives on the circumcircle. So if you reflect it through side AC, it's the circumcircle there and the circumcircle here. And there's exactly one point in the triangle that does this. It's the orthocenter. And yeah. We'll talk more about orthocenter soon enough. But with that, we now have what? We have the circumcenter, we have orthocenters, and if you've been looking at the homework, the very first problem on the homework talks about the intersection of the three medians, proving that the three medians are concurrent at a single point, which is called the centroid. So this is 2B. Really quite a short section. We'll see what we can do right now. Yeah, so in every triangle, the three medians are concurrent at a single point at a point known as the centroid. Of the triangle. How do we know this? Well, this is one of your homework problems. So this is homework 1H.2, the first problem. By the way, I know that you've seen this word before. Where else in math have you seen the word centroid? Do you recall centroids of figures before? Calculus, Cal 2, even Cal 3. Finding centers of mass of thin plates. If you have a plate of uniform density, so density is the same at every single point, then the center of mass of the plate is usually called the centroid. And it's the exact same centroid as we're talking about here, so we'll relate maybe next class about how the center of mass relates to this concurrency point between the three medians. But anyway, this is homework 1.8.2, showing this fact. I'm going to prove a stronger result. Not only are they concurrent, but I can tell you exactly where the centroid is. So, the three medians of an arbitrary triangle. This is nice, right? I'm not restricting to acute angle triangles here or anything. Arbitrary triangle are concurrent at a point. So same thing you have right here. There's 1.8.2. We're going to go further. I'm going to tell you where this point is. Concurrent at a point that lies 2/3 of the way along each median. The only question is which direction am I talking about? So 2/3 of the way along each median from the vertex to the opposite side. From the vertex of the triangle toward the opposite side. So what I'll say now is of course, we're proving something even stronger than your homework result. So technically, if I didn't say this right now, I suppose I wouldn't be able to fault you for just taking this proof and copying it and turning it as your homework, because you're proving the homework result. So what I'll say right now is don't do that, right? The method of proof for your homework is given by a hint. It says use this previous problem. So please prove it that way. Don't just give me this proof back. And I'll just erase everything here so I have a lot of space. And we'll write a proof. Let's see. We'll draw in some stuff. So, arbitrary triangle. Even though it's arbitrary, I'm going to draw an acute triangle because they look better. A, B, C. And we'll drop in, let's try to go with the actual median, so there's the midpoint X. We'll draw in the median AX. And I'm going to give you one more median here. We'll draw in the median from B, so let's see, let's try and find the midpoint, maybe right there. So we'll draw on the median BY, and we'll call the point of intersection between them. That's of course going to be what the centroid is. Almost universally people use the letter G for centroid, so we'll go with G. I don't know why G, must come from Greek or something, but yeah. So let G be the intersection of medians AX and BY. What do I want to show? Well, I want to show that G lives 2/3 of the way down this line, right? So in other words, I want to show that AG is twice as long as GX. So AG is twice as long as GX. But I'm actually not going to show that. I'm going to show that 1/2 AG is GX. Same thing. Just yeah, I suppose it's maybe it's a bit more clear if you write it this way. It's more obvious to see that that means it's 2/3. We can multiply by 2 at the end. Are you guys okay with that? If I can show that this is twice as long as this guy, then that means it's 2/3 down the whole line. Okay, so that's what I want to show. What are we going to do? We're going to draw in XY. So here's XY. My claim is that XY is parallel to AB. Why is that? Well, that's our invoking that lemma. This is a median, so I know CY is exactly half the length of CA, and CX is exactly half the length of CB. So, because these sides are sort of proportional in length, our lemma says that XY must be parallel to AB. So draw XY, and note that CY over CA, that's 1/2. Which is CX over XB. So that means these two lines are parallel. XY is parallel to AB. Also, that of course establishes that the smaller triangle CYX is similar to CAB. And I'm going to label these vertices in a different order, but also triangle, we went with this one. CYX is similar to triangle CAB. With scale factor, as we've just shown, with scale factor 1/2. So, in particular, the only side we haven't looked at, XY, is half the length of AB. Okay, so XY is half the length of AB. Two facts that we'll use later on down the road. What else?
I have a question.
Yes.
When you have CY over CA is equal to 1/2, and you have that equal to CX over XB, do you mean that as CX over XB, or do you mean that as CX over CB?
I mean CX over CB. Thank you very much. I wonder if I made a copy. Yeah. I shouldn't just blindly believe my notes. CX over CB. So what am I trying to do here? Well, I'm actually trying to show that this triangle GYX is similar to GBA. And that's what I'm trying to do. And the reason I made this observation here is because now I know that at least this side is 1/2 of this side. So what else can I do? Well, I can actually I can figure out something about these two angles. Because I know XY and AB are parallel, I know that this angle here is congruent with that angle there, because they're alternate interior angles. So now, because XY is parallel to AB, and because they are alternate interior angles, we have that angle ABY is equal to angle XYB and these other two alternate interior angles are equal. So angle and call it BAX is equal to angle YXA. And I can't remember what I just said. Did I lie to you guys? Did I say ASA? I was thinking ASA in my mind, angle, proportional sides, angle, but of course ASA isn't really a condition for similarity. Well, we don't state it because it obviously is, because I don't need ASA, I just need AA, right? If two angles are the same, the third angle must be the same, they're similar triangles. So by AA, we have that triangle GYX is similar to triangle GAB. Getting the order there right. So there's where we use this fact, right? We use the fact that those two lines are parallel to show that they're similar. What else have we done? What's my scale factor between these? Well, we've already seen that this side is half the length of this side, so our scale factor is 1/2. So triangle finally, because XY is 1/2 of AB, we have, let's just say it follows that GX is 1/2 of AG. Which is exactly what we wanted to show, right? That 2GX is AG. As desired. I suppose I'm not really finishing the proof, but we're just about out of time. What else do I need to show? I need to show that that is 2/3 of the way along, so this side's twice as long as this. And if I drop in a median there, that of course it cuts through G, and then this is 2/3 as long. But I think we'll just stop here in the interest of time. So it's really just saying similarly. Using similar methods of proof, you can show all that stuff. So similarly, G is 2/3 of the way along the other medians as well. All right, if I want to show it lives 2/3 of the way along, say, CZ, well, now I'm looking at similarities between this triangle and, where's my other triangle? Oh, and this triangle. So it really is just doing the same proof again. Any questions? All right, so this is a stronger result than your homework. Your homework just wants you to show that the three medians intersect at a point. Use the suggested method of proof. This one's stronger. This tells us not just that they intersect at a point, known as the centroid, but it tells us exactly where that centroid lives. It's 2/3 of the way along any median that you want. And you can't just use this proof for homework. All right, I want to say a little bit about the exam. Do you guys know when the exam is, first exam? It's, I believe, 2 weeks from Friday, so a little bit more than 2 weeks from today. I'll talk a bit about it on next class, I guess. So we'll stop here, and I'll see you guys.